Welcome to month 3 of the Senior DevOps Engineer track. Today, we're building on the Kubernetes and GitOps foundations from months 1 and 2, and adding an entirely new security layer, the service mesh and zero-trust networking. By the end of the session, you will have enforced mutual TLS across every pod-to-pod call, expressed your service access matrix as code, and built a default deny network posture that holds even when things go wrong. The session runs 4 hours. Hour 1 covers mesh architecture and the mTLS migration pattern, how Istio works, and how to move from permissive to strict mode without downtime. Hour 2 is authorization and network policy, the actual security posture. You will implement authorization policy at the workload identity level and network policy at the kernel level. Hour 3 is the hands-on challenge, where you apply everything to the BISTEC Mart scenario. And Hour 4 covers traffic shaping, canary rollouts, fault injection, and mirroring, plus the diagnostic toolkit for when things go wrong. Before we start, check that your kind cluster is running with Cilium as the CNI. KindNet, the default kind CNI, silently ignores network policy. Using it means your network policies look applied, but enforce nothing. A service mesh has 2 planes. The data plane is the envoy sidecar injected into every pod. It intercepts all inbound and outbound traffic via an IPTables redirect rule. The application itself sees plain HTTP and is unaware of the mesh. The sidecar handles mutual TLS, authorization enforcement, and telemetry on the application's behalf. The control plane is Istio, which has 3 components. Pilot translates Istio custom resources, virtual services, destination rules, authorization policies, into envoy configuration and pushes it to every sidecar via a streaming gRPC connection. Citadel is the certificate authority. It issues a SPIFFE SVIDs bound to Kubernetes service accounts and rotates them every 24 hours. Galley is the validation webhook that rejects malformed Istio resources at admission time. Istio 1.22 introduces ambient mode, which removes the per-pod sidecar requirement. As tunnel daemon set handles layer 4, and opt-in waypoint proxies handle layer 7. No pod restart needed on install, and memory overhead is lower. Ambient mode is newer and less battle-tested than sidecar mode. Choose deliberately. The mesh tax is real, roughly 3 to 5 milliseconds of P999 latency per hop, and 50 to 100 megabytes of RAM per sidecar. This is the right trade-off for services that need zero trust, but not every service in your cluster does. The mTLS migration follows 3 steps and must be executed without downtime. The first step is applying permissive mode cluster-wide. In this mode, sidecars accept both plaintext and mTLS connections. Your existing callers keep working while you roll out sidecar injection across namespaces. The second step is verifying injection. For every pod in every namespace, confirm that Istio proxy appears in the container list. Any pod that doesn't have a sidecar will break mTLS once you flipped strict. Find them now and restart them with injection enabled. The third step is flipping to strict. Do this namespace by namespace first. Apply a strict peer authentication to one namespace. Verify in Kiali that every service edge shows a green mTLS lock, then move to the next. Once every namespace validates, replace them all with a single strict peer authentication in Istio system. That single manifest enforces mTLS on every workload in the cluster. If a legacy namespace can't be migrated immediately, you can keep it in permissive with a namespace scoped override. This is a temporary measure. Document it and revisit. If you flip a namespace to strict, while one of its pods still lacks a sidecar, every call to and from that pod returns 5 month 3. The mTLS handshake fails. because the pod can't present a certificate. In a zero-trust mesh, identity is cryptographic, not network-based. Istio's Citadel signs an X509 certificate, called a SPIFFE SVIDD, for every pod bound to its Kubernetes service account. The URI follows the format spiff://cluster.local/ens/the namespace name/sa/the service account name. Think about this. IPs are ephemeral and spoofable. Pods restart and get new IP addresses. In an autoscaling cluster, maintaining IP-based firewall rules is continuous operational debt, and it provides weaker guarantees than certificate identity. A service account, by contrast, is stable and auditable. It's tied to Kubernetes RBAC. The certificate rotates automatically every 24 hours. And when you reference a principal in authorization policy, you're referencing the cryptographic identity in the cert, not an IP that could have been reassigned. The flow is: pod starts, Istio issues SVID, Envoy presents that certificate on every outbound connection. The receiving envoy extracts the principal from the cert and passes it to AuthorizationPolicy for evaluation. Two practices that follow from this: create a dedicated service account for every microservice and never share the default service account. And disable auto-mounting of the service account token where it isn't required. It reduces the blast radius if a pod is compromised. Authorization policy is your Layer 7 access control layer. The example on screen allows the storefront service to call catalog's product API using GET and POST, and only those methods on paths matching the API product's prefix. The from source principles field references the SVID principal exactly. This means only a pod running as the storefront service account in the BISTEC Mart namespace can make that call. A compromised pod with a different service account identity is denied, even if it can reach the port. There are 3 levels of rule granularity. The principals field matches the exact workload identity, the most precise control. The namespaces field allows any workload in a listed namespace, cursor, useful for internal tooling like monitoring. The operation field restricts by HTTP method and path. This is how you block deleted calls from services that should only read. The critical prerequisite: principal-based rules require mTLS strict to be active. In permissive mode, plain text callers present no certificate, so the principals field has nothing to match against, and the rule is silently bypassed. Always enable strict before relying on authorization policy for security. To establish a default DNI posture, apply an authorization policy with no rules to each namespace. An empty rule set means deny all. Then add explicit allow policies on top. NetworkPolicy operates at Layer 3 and Layer 4, IP address and port. It is enforced by the CNI kernel module before traffic reaches any envoy proxy. This makes it complementary to authorization policy, not redundant. NetworkPolicy blocks lateral movement, even when a sidecar is missing or misconfigured. The default DNI manifest has 2 lines of specification: an empty pod selector that matches all pods in the namespace, and policy types listing both ingress and egress. With no ingress or egress rules specified, the result is deny all. From that baseline, you add explicit allow rules. DNS egress. Allow outbound UDP and TCP on port 53 to the Kubernetes service. Without this, pods can't resolve service names by hostname. Prometheus scrape ingress. Allow inbound traffic from the monitoring namespace on port 9090. App to app. Allow inbound traffic from pods labeled app storefront to the catalog service on port 8080. A critical sequencing note: apply the DNS egress allow before applying the default DNI policy, or every pod immediately loses name resolution. The safest approach is to apply the allow policies and the deny policy in a single kubectl apply command. The CNI requirement bears repeating. KindNet, the default kind CNI, accepts NetworkPolicy objects and ignores them entirely. There is no error message. Your policies look applied but enforce nothing. Use Cilium or Calico and verify that CNI pods are running in kube system before trusting any network policy. Network policy and authorization policy are not redundant. Each catches failure modes the other misses. Network policy, enforced by the CNI kernel module, stops lateral movement at the lowest level. It works regardless of whether a sidecar is present. But it has no concept of HTTP. It can't distinguish a GAT from a delete, or recognize which service account the caller is running as. Authorization policy, enforced by the Envoy sidecar, understands HTTP verbs, URL paths, JWT claims, and cryptographic workload identity. But it requires the sidecar to be present in the traffic path. If injection has been missed for a pod, authorization policy is never evaluated for that pod's traffic. Combining both layers means a compromised pod can't reach non-allowed services via raw TCP, and even a pod presenting a valid certificate can't call restricted HTTP endpoints. The sidecar resource adds a third level of control. Without it, every Envoy sidecar learns routes to every service in the cluster. That's unnecessary memory consumption and an expanded lateral movement surface. A compromised sidecar could probe services it has no business reaching. Adding a sidecar resource and restricting egress hosts to only the services this workload actually calls closes that surface. Virtual service is how you shape traffic without modifying deployment manifests. The weight-based canary example routes 90% of requests to the stable subset and 10% to canary. To shift that ratio, you update a single YAML field and kubectl apply. No rollout. No restart. Header-based routing lets you target a specific subset of users. In the example, requests carrying the header X beta user, true, are routed to the canary version. All other traffic goes to stable. This is ideal for internal validation. Route your own team's traffic to the new version before exposing it to all users. Mirroring copies live traffic to a shadow service and discards the responses. The primary caller receives the stable response. The shadow receives a duplicate of the request and does whatever it wants with it. Use mirroring to test a new version under real production load without any user-visible risk. One dependency that catches people. You must create a destination rule that defines the stable and canary subsets by mapping to pod labels before creating the virtual service that references them. If the subset doesn't exist in a destination rule, Envoy has no backend to route to, and every request returns 503. Fault injection is how you verify that your services are actually resilient, not just theoretically designed to be. The delay injection example adds a 5-second fixed delay to 50% of calls to the catalog service. Use this to verify that your client enforces its timeout configuration. Without an explicit timeout set, callers queue indefinitely and consume threads while waiting. That is the exact cascading failure pattern that causes cluster-wide outages under partial failure conditions. The abort injection returns HTTP 503 to 20% of requests. Use this to verify that retree logic is bounded and that circuit breakers trip at the expected thresholds. Unbounded retrees under partial failure amplify load on an already struggling service. They make partial failure worse, not better. For graceful degradation testing, inject errors on a non-critical dependency and verify that the calling service serves a fallback response rather than propagating the failure to users. To keep production traffic safe during lab exercises, scope faults with a header match. Adding a condition that only injects when xchaos test true is present in the request means real traffic is never affected, even if a fault injection rule is accidentally left applied. When something breaks in the mesh, you have three primary diagnostic tools. The first command to run is always Istio-analyze. It validates every Istio resource in the namespace against known rule sets and reports specific problems. A missing sidecar, a virtual service referencing a non-existent destination rule subset, conflicting peer authentication scopes. Run it before doing anything else. It often identifies the root cause in seconds. The second tool is Istio proxy config. The root subcommand shows the computed envoy routing table for a specific pod after all virtual service and DestinationRule resources have been translated. Compare what envoy has computed against what your virtual service specifies. Discrepancies reveal translation errors or missing destination rules. To verify that mTLS strict is active on a specific listener, use proxy config listeners with the port flag, output as JSON, and grep for tils mode. Look for Istio mutual in the filter chain. Envoy access logs are your per request record. Filter out the 200 responses and look at the response flags on everything else. UAX means the request was denied by an authorization policy. NR means no root was found, usually a missing or mismatched destination rule subset. UF means the upstream connection itself failed. Two failure patterns appear constantly. The first is a missing sidecar in a strict namespace. The mTLS handshake fails immediately and every call to or from that pod returns 503. Fix by enabling injection on the namespace and restarting the affected pod. The second is a virtual service that references a subset not defined in any destination rule. Envoy has no backend for the root and returns 503 with NR Istio-analyze catches both of these before you touch any traffic. Kiali is your service graph and configuration validation console. It reads from Prometheus and the Kubernetes API to render a real-time topology of your mesh, with per-edge metrics. The most important visual indicator is the lock icon on each service edge. A green lock means mTLS strict is active on that connection. A gray icon means permissive mode or plain text. When you flip the cluster to strict, Kiali gives you immediate visual confirmation that every edge is secured without running any kubectl commands. Kiali also surfaces request rates, error rates, and P99 latency per edge. During an incident, this lets you identify which service-to-service call is failing before opening a single log file. For structured dashboards, Grafana dashboard IDs 6639, 76636, and 11829 are pre-built for Istio metrics and ready to import from grafana.com. They cover the service layer, the Istio control plane, and individual workloads respectively. For distributed tracing with Jaeger or Zipkin, Istio's Envoy sidecars auto-generate spans for every proxied request. The only requirement from your application code is propagating the X requested and XB3 treeseed headers between service calls. When you do that, traces stitch together across services automatically. The challenge uses the BISTEC Mart scenario. 3 microservices, storefront, catalog, and payment, run on a kind cluster with Cilium. Istio is installed in permissive mode. Your task is to harden this cluster to zero trust without taking the storefront offline. There are 4 deliverables, each worth 25 points. Deliverable 1 is the mesh install and strict mTLS. Verify sidecar injection in the BISTEC Mart namespace. Apply a cluster-wide strict peer authentication, and confirm all 3 services show the mTLS lock icon in Kiali. Provide kubectl output as evidence. Deliverable 2 is the authorization policy access matrix. Allow storefront to call catalog on GET to the product API and payment on POST to the payment endpoint. Deny all other cross-service calls. Test with curl from each pod and document both the allowed and denied results. Deliverable 3 is the default deny network policy. Apply the deny all policy and add explicit allows for DNS egress, Prometheus scrape ingress, and storefront to catalog on port 8080. Validate with netpol tester or kubectl exec. Deliverable 4 is the canary and fault injection demo. Deploy catalog version 2. Configure a 90-10 virtual service split. Inject a 2-second delay on 30% of catalog calls. And verify that Grafana shows the split and that the storefront handles the delay with a configured timeout. The scoring is 25 points per deliverable for a total of 100. For deliverable 1, the primary evidence is a Kiali service graph screenshot showing green mTLS locons on all edges. For deliverable 2, curl output from each pod to each target, both the successful call and the denied call with a 403, confirms the access matrix works as designed. For deliverable 3, a netpol tester report or kubectl exec connectivity test documents which paths are open and which are blocked. For deliverable 4, a Grafana screenshot showing the 90-10 traffic distribution, alongside a Kiali or curl trace showing the fault injection delay, constitutes full evidence. All YAML manifests go into a feature branch, committed and pushed before the pull request. Include a results SND that summarizes each deliverable with your evidence. Have a colleague review before submitting. For those who finish early, the offline milestones are valuable. Try linkered on the same workload and compare sidecar memory to Istio. Migrate one namespace from sidecar mode to Istio ambient mode. Or add a Spire trust domain for a non-Kubernetes workload, such as a VM or a CI runner. 6 mistakes appear consistently in service mesh labs, and knowing them in advance will save you significant debugging time. The first is forgetting a sidecar in one namespace. A single uninjected pod in a strict cluster breaks mTLS for every connection to and from it. Run Istio analyze immediately after enabling injection in a new namespace to catch this before traffic flows. The second is using kindnet instead of Cilium or Calico. Kindnet silently ignores NetworkPolicy objects. No error, no warning, no enforcement. Verify your CNI by checking for Cilium or Calico pods in the kube system namespace before trusting any network policy. The third is writing a virtual service before creating the destination rule. The subset references in the virtual service resolve to nothing. Envoy has no backend, and every request returns 503 with the NR response flag. Always create the destination rule first. The fourth is enabling principal-based authorization policy rules, while the cluster is still in permissive mTLS mode. Plain text callers present no certificate, so the principals field never matches and the rule does nothing. Enable strict first, then write your authorization policy. The fifth is applying default deny without a DNS egress allow. Every pod immediately loses the ability to resolve service names by hostname. Apply the DNS allow rule in the same kubectl apply operation as the deny policy, or apply it first. The sixth is sharing the default service account across workloads. One compromised pod can then impersonate the identity of every other workload in the namespace. Create a dedicated service account per microservice and disable token auto-mounting where it's not needed. Here is what you have covered in month 3. You understand the Istio data plane and control plane, and when sidecar mode versus ambient mode is the right choice. You can execute a zero downtime migration from permissive to strict mTLS. You can express a service access matrix as authorization policy, backed by SPIFFE cryptographic identity, rather than IP addresses. You can implement default DNI networking at the kernel level with precise allow lists. You can shape traffic with canary weights, header-based routing, fault injection, and mirroring. And you have the diagnostic toolkit, Istio to analyze, proxy config, and envoy access logs to find mesh failures quickly. Month 4 moves into reliability engineering, defining SLIs and error budgets, implementing Prometheus alerting rules tied to real SLOs, and running controlled chaos experiments with Chaos Mesh and Litmus Chaos. For your offline study this month, read NIST SP ADRA 207, the foundational Zero Trust architecture document. Try linkered on the same BISTEC Mart workload and compare its operational overhead to Istio. And when you are ready, migrate one namespace from sidecar mode to Istio ambient mode and measure the memory difference. Well done on month 3.